All right, do I hear myself? And do I see my hand moving in front of the camera? Yep. Okay, then we are good to go. Headphones have been put away. Kind of like yesterday, I'm feeling kind of tired, but I want this to be done, so we will press forward. I drank some green tea. Hopefully that will help keep my, what's the word I'm looking for? Hopefully that will help me kind of stay focused enough to not make any blatant mistakes. Hopefully there will be fewer of those brain malfunction moments that we witnessed yesterday. But without further ado, let's begin. So yesterday we introduced the concept of momentum, and we also introduced impulse, and we went over the impulse momentum theorem. We talked about graphs of force versus time and momentum versus time and what kinds of information you can get from those graphs. And we concluded with a discussion of conservation of momentum and the condition for it. And we compared that to conservation of mechanical energy. And we emphasized that conservation of mechanical energy and conservation of momentum are completely independent. It is possible to have situations where both are conserved, situations where neither are conserved, and situations where only one or the other is conserved. Neither one of them being conserved implies that the other one is conserved. They have two completely separate conditions, and you need to examine each condition separately. Other than that, what else did we do? We kind of touched on elastic collisions and what they are. Basically, collisions in which energy is conserved. That's just the definition. And as a consequence of that, we have two equations that we can work with. And I gave you some homework yesterday at the end of the stream where I tasked you with deriving this, combining these two equations to derive this, and I also noted some other forms that you might get in your derivation before you get it into this form. I am not going to do the derivation here because I already did it way back when we did the Math Essentials in the first two streams of this course. I believe it was somewhere towards the end of the first stream and the beginning of the second stream, if memory serves. So that has already been done. I'm not going to redo it for you. Instead, we're just going to start off from here, and we're going to talk about why I prefer having it written in this form and what the physical meaning of that is. And what else do we have on our agenda for today? Oh goodness, that is not good. What's my screen doing? Huh. Okay, let's see. Okay, that works. My screen has been acting up today, and I'm not sure why. Maybe it's some sort of graphics card update, but like I get sometimes random flickering pixels on my screen. Anyway, on our agenda for today, we're going to continue what we started at the end yesterday with elastic collisions. We're going to talk about inelastic collisions, which come in two types. And then we're going to talk about an application that combines both momentum and energy called the Ballistic Pendulum. Then we're going to look at collisions involving more than two objects. And finally, we are going to talk about two-dimensional collisions, and somewhere along the way, we are going to do some problems that combine what we've learned about momentum with previous topics, kinematics, force, energy, all that stuff. Uh-oh, what is going on with YouTube? It says, error, YouTube is not receiving enough video to maintain smooth streaming. As such, viewers will experience buffering. Okay. That's fine by me, as long as the whole thing actually ends up showing up. Wait. How do I put this back up? There we go. Oh my, so much seems to be going wrong today. Stuff is flickering on the screen and I do not know why. What is happening? Oh my goodness. Well, that's why I also record while I stream. If the stream just looks all garbled up and messed up, I will just re-upload the recording. If something messed up is going on for those of you who happen to be watching this live, sorry, but you'll just have to wait for the recording to be posted. And if nothing is going wrong, well then congratulations, you don't have to wait. Anyway, let's go ahead and start with this topic of elastic collisions. So when we combine the conservation of momentum equation with the conservation of mechanical energy equation, which doesn't have potential energy in it because we're usually just talking about simple one-dimensional collisions where there's no change in height, so no gravitational potential energy, and there's usually no springs involved either, so there's no elastic potential energy either. Usually the energy that's being conserved in elastic collisions is kinetic energy only. And if we combine those, we do a little bit of algebra, we end up with this thing. And what is this? V1 initial minus V2 initial equals the negative of V1 final minus V2 final. So let's go ahead and talk about relative velocity. Relative velocity. Not really the most important topic in AP Physics, but I do have some book problems that mention it, and in order to be able to do those problems, we do kind of need to understand the concept. I have hinted at it before, I think, especially when discussing static and kinetic friction. I mentioned that static friction isn't for objects that don't move, it's for objects that don't move relative to the surface that they are in contact with. Two objects will have a relative velocity of 0 if they are moving at the same speed. If you, sitting down in your chair right now, or standing up as the case may be, I don't know if you're watching this sitting or standing, but I would probably recommend sitting. But yeah, you're standing on a planet that's rotating around its own axis at really high speeds. You don't feel it. You feel like you're stationary because even though the earth underneath your feet is moving, you're moving just as fast. So relative to the earth, if you're just sitting still or standing still as the case may be, your velocity relative to the earth is 0. So how do I get the relative velocity between two things? Well, it depends on who you ask. If you ask Galileo, it's a simple matter of subtraction. If you ask Einstein, it's more complicated. You can learn about that stuff in AP Physics too. We're going to take Galileo's perspective, Galilean relativity. Basically, if you subtract the velocities of two objects, you get the relative velocity between them. You might remember, actually, it's coming back to me, in kinematics, I think we did a problem, if I'm not mistaken, where there were two cars and one car was chasing the other car and they both had constant velocities. And I think if we did do that problem, then I'm pretty sure I would have commented on how the difference in velocity between the two objects is the speed at which the distance between them is shrinking. That was a relative velocity, even if you didn't realize it at the time. This is all assuming I actually did that problem. I might be getting my stream problems, my on-stream problems, confused with problems I did with my actual private students. So if none of that is ringing a bell, then I might just be misremembering what I actually covered. Anyway, V1 initial minus V2 initial, what's this? This is the velocity of object 1, the initial velocity of object 1, relative to object 2. This is the relative velocity between the two objects before they collide. It's the relative velocity between them before they collide. And with the way I've drawn it, V1 initial minus V2 initial would essentially be just the rate at which this gap between them is closing. Right? The faster object 1 is, the faster this gap closes, and then the faster object 2 is, the slower it closes. So it makes sense that you would have the positive of this minus whatever this is, and then the difference between the two would be the relative velocity. If they were both at the same velocity, then the distance between them wouldn't be shrinking at all. That's another way to think about it. So V1 initial minus V2 initial. This is the initial velocity of object 1 relative to object 2. Okay, what about V1 final minus V2 final then? Well, that is the relative velocity of that's the final velocity of object 1 relative to object 2. And you'll notice there's a negative out here. So what is this saying? What this is saying, and we'll prove this mathematically with a problem, we'll get to, well, not prove so much as demonstrate this mathematically with a problem. What this is saying is that the relative velocity before and the relative velocity after collision, when energy is conserved, for elastic collisions only, the relative velocity has the same magnitude, but the negative sign tells you that the direction is different. That is, after collision, whatever rate this distance between the objects was shrinking at, this distance is closing at a certain rate. After they collide, they begin to separate, and the rate of their separation, the distance between them, will grow at the same rate that it was shrinking at before the collision. That's really what this problem is saying. So if you can remember that, if you can remember that these are relative velocities, if you can remember this as relative velocity before equals the negative of relative velocity after, and if you also remember just how to get relative velocity of one object to another, then that makes it easier. You don't have to necessarily memorize the order of these variables. You can simply summarize this as V relative initial equals negative V relative final. Let's go ahead and give a couple more examples, maybe one or two simple ones for relative velocity. So let's say I have, a person standing still, quote unquote, and then another person, let's say they're on a train, and let's say this person inside the train is running forward, and then the train itself is also moving forward. Let's say the train is moving at, I don't know, V train equals, how about 8 meters per second? I don't know if that's too fast or too slow for a train, but we'll go with it. And let's say that this person, ignorant of the train's speed, perceives themselves as moving V, let's see, I guess V passenger, I'll just abbreviate it, V pass. V passenger. Let's say this person perceives themselves as moving at a rate of 3 meters per second. And of course this person is sitting still. So one of these velocities given is already a relative velocity. So everybody's velocity really depends on who you ask. Let's go ahead and figure out what the velocity of everything is relative to the ground. Relative to the ground, we have, oh, and I see that little warning on YouTube is gone, so I hope that means that the stream is back to normal, if there was anything abnormal about it to begin with. Anyway, where was I? So let's figure out everybody's velocity relative to the ground. So I guess we'll call this person the observer. The observer relative to the ground, well, that's going to be 0. Okay, and the velocity of the train that I gave, that's also given relative to the ground. That's according to what this person sees. This person outside sees the train moving at 8 meters per second. So the train that was given to us is also relative to the ground. And that's 8 meters per second. But V passenger, I said this was from the perspective of the passenger. So what is V passenger relative to the ground? That's what we want to find out. So what we have right now, this V pass of 3 meters per second, this is actually their velocity relative to the train. V pass relative to the train equals 3 meters per second. So what I can do is I can rewrite this as V passenger relative to some third thing, in this case the ground, minus, and I guess I don't have enough room for this, but V, I'll just say T for train and G for ground. V train relative to the ground. So that means the 3 meters per second that this passenger perceives themselves as moving at is actually going to be their speed relative to the ground minus the speed of the train relative to the ground. So that's going to be V passenger relative to ground minus V train relative to the ground is going to be 8 meters per second. And that tells us then that V passenger relative to the ground, just add the 8 to both sides, V passenger relative to the ground must be 11. V passenger relative to the ground must be 11 meters per second. So whenever you're trying to calculate relative velocity between two things, at least using my notation, I would say the velocity of thing 1 relative to thing 2, whatever comes after relative to, whatever comes after the words relative to, so here you'll have object or person 1, thing 1, and then thing 2. And if I ask for velocity of, thing 1 relative to thing 2, whatever comes after relative to, that's the one whose velocity you subtract. So to get the relative velocity between two things, you need to subtract both of their velocities relative to some third thing. In our case, the third thing would be the ground. That's our usual, what we call, frame of reference. So if you hear that term, frame of reference, your frame of reference is basically the perspective of the second thing that you're moving relative to. So in the ground or earth frame of reference, we would be looking for velocities relative to the ground. In the train frame of reference, the train's velocity would be 0, right? The velocity of something relative to itself will just be 0. And then the velocity of the passenger will be, let's see, I guess it will be 8 minus 11. So from the train's, wait, is that right? Now I'm confusing myself. Oh, great. So from the train's frame of reference, it's as if it's moving at 0 meters per second from its own perspective. V train relative to train is 0. V passenger relative to the train would be V passenger relative to the ground, which is 11, minus, yeah, right, V passenger here is relative to the train. My brain is malfunctioning already. Yeah, we are off to an excellent start, aren't we? Let me figure out where I was going with this. So if we wanted to calculate everything's velocity relative to the train, V train relative to train would be 0. V passenger relative to train is the 3 meters per second that we got. So this person is perceiving the train as stationary, and that's why they see themselves as moving at 3 meters per second relative to the train. And then the observer, from the train's perspective, if the train sees itself as stationary, then from the train's perspective, this observer is actually moving to the left. The train pretends that it's the stationary one, meaning that the observer is moving backwards from its perspective. So that's going to be 0 minus 8. So this person, the observer relative to the train, would be V observer relative to the ground, 0, minus V observer, or minus V train relative to the ground, 8. It's going to be moving at negative 8 meters per second from the perspective of the train. And we could keep going on with this. We could add one more thing. Let's say we could add, say, a driver moving at some velocity relative to the ground, somebody in a car moving at whatever velocity relative to the ground, V car, ground, Do I even have enough space to write the word ground? Not really, I kind of smudged it, but you know what it's supposed to say. And you could give them a velocity and just add more to this problem and figure out what everybody else's velocity is going to be from the perspective of this driver, or what this driver's velocity is going to be from the perspective of the observer, or the passenger, or the train. There's a lot you can do with this. I would recommend just practicing with the concept a little bit until you can do it kind of mindlessly, kind of intuitively. But yeah, that's relative velocity, at least basic relative velocity for things that move relatively slow. Yes, cars moving at 100 miles per hour are still considered slow, because in physics, slow means very, very small fraction of the speed of light. In physics, something is truly moving fast when it's approaching a significant fraction of the speed of light. That's when things get a bit weird, and then Galilean relativity no longer applies. But again, that's a Physics 2 topic. If you ever decide to take AP Physics 2, we are not going to cover that today. So that's relative velocity. We might see a question or two that mention it, so it's good to just know how to calculate it. And it also just helps you simplify this equation so that it's not some sort of mishmash of 4 symbols that are very hard to remember in order. It's much easier to remember this equation as this: v relative initial equals negative v relative final between the two objects. And come to think of it, it doesn't even matter which object you consider to be object 1 and object 2 here. The equation would still work just fine if I calculated the relative velocity of object, object 2 to object 1. I would do v2 initial minus v1 initial equals the negative of v2 final minus v1 final. I would just reverse the order of subtraction on both sides of the equation. That's fine. Reversing the order of subtraction just gives you the negative of the original. So I'm basically just, by reversing the subtraction on both sides, I'm just multiplying both sides by -1. So it's perfectly mathematically valid. So decide on one object that will be like the object whose frame of reference you're taking, and then calculate the velocity of the other object relative to the first, both before and after the collision, and there's your second equation. So from now on, instead of having to invoke kinetic energy for elastic collisions, anytime you have 2 unknowns, use this equation with this equation, after of course expanding it to this, and now you have 2 simple linear equations that are much easier to deal with algebraically when solving for 2 unknowns. Okay, let's do an actual problem and put what we just learned to good use. Let's dig up a problem. Okay, so here's one. It says a 10 gram object (10 grams, not kilograms), a 10-gram object moving to the right at 20 centimeters per second, moving to the right at 20 centimeters per second, makes an elastic head-on collision with a 15-gram object moving in the opposite direction at 30 centimeters per second. So we have a 15-gram object moving in the opposite direction at 30 centimeters per second. So this is the before picture, and I'll draw some sort of smooth, frictionless surface underneath them. So this is before collision. And then we're going to have another picture for after collision. There's our 15 grams, there's our 10 grams. I would imagine I'm going to predict that the 10-gram object is going to end up moving to the left, and the 15-gram object I think will still be moving to the left, just slower. At least that's my prediction, but we will do the math and figure out what actually happens in the end. These are just my predictions for now, so don't put too much stock into the direction of these arrows or their lengths just yet. Okay, so normally I would convert centimeters to meters and grams to kilograms, but in collision problems, a lot of times we can get away with not doing that. As long as the units agree with each other, we're not really going to have problems, because whatever units we have are going to cancel out, or if we're solving for some unknown, it will come out in the units that we actually put in, as long as our mass units that we put in are in agreement with each other, and the velocity units that we put in also are in the same units. I will write out the units in the equation this time just to show and illustrate that that is the case, that we can get away with not converting to standard units for these types of problems. So it says find the velocity of each object after the collision. Find, I guess we'll call this V1 final, and we'll call this V2 final. And this, of course, would have been V. Well, let's write down what we know. So M1, object 1, is going to be 10 grams. M2, for object 2, that's going to be 15 grams. V1 initial is going to be positive 20 centimeters per second. I'm going to say that right is the positive direction. And V2 initial is going to be negative 30 centimeters per second. I did warn about this yesterday. Remember to decide on a positive direction before you start your momentum problems. Make sure you remember to do that. Very, very easy mistake that students make all the time in this chapter. Remember, you will be given speeds most of the time and not true velocities. You have to take direction into account, and in the one-dimensional case, you have to slap on a negative sign whenever it's needed. Okay, so we can go ahead and write our conservation of momentum equation, M1 V1 initial plus M2 V2 initial, the total momentum before, equals M1 V1 final plus M2 V2 final. We could have had, let's see, so total momentum initial plus the change in momentum, which should be 0, right? We discussed that yesterday. Momentum is conserved when change in momentum is 0, but in cases where momentum is not conserved, you would just put a plus delta P on this side of the equation, and it works pretty much the same way that our conservation of energy equation worked in the previous chapter. So if I go ahead and work with my masses, what do I get? If I go ahead and substitute their values, I get 10 grams times V1 initial is 20 centimeters per second plus 15 grams times negative 30 centimeters per second equals 10 grams times we don't know yet plus 15 grams times we don't know yet, V2 final. Well, you can probably see from here if I divide the whole equation by grams, the grams cancel out. And so whatever my V1 final and V2 final are, first of all, for addition and subtraction, the units have to be the same in order for me to be able to add them. So whatever units they are, they must be the same as each other. And also whatever units they are, they must equal the units on the left. The only units I have left on the left are centimeters per second. So that tells me that V1 final and V2 final are going to come out in centimeters per second. So like I said earlier, we do not actually have to convert to standard units for most of these problems. Only time we have to do that is like when one object has its mass given in grams and the other is in kilograms, or one object has its velocity given in meters per second while the other one is in centimeters. In that case, yeah, we do have to convert in order for the units to agree with each other, or else these cancellations just don't end up happening and you just get these weird messed up units. Anyway, we need a second equation because we have two unknowns. So V relative initial equals negative V relative final. V relative initial between the two objects equals negative V relative final. That is to say, I'm gonna do, let's see, I want to do velocity of object 1 relative to velocity of object 2. So V1 initial minus V2 initial equals the negative of V1 final minus V2 final. That's what I'm going to do. So that's going to be 20 in centimeters per second minus V2 initial is negative 30 centimeters per second. We can quickly do the math here and check. If this thing is going at 20 centimeters per second to the right, and this one is going at 30 centimeters per second to the left, 20 minus negative 30, it does make sense that when two things are coming at each other, those both contribute to closing the gap between them faster. So I would expect the relative velocity between them to be greater than the magnitude of either one of them. So yes, getting 50 centimeters per second, that makes sense to me. If you were driving a car at, well, maybe not centimeters, if you were driving a car at 20 meters per second and you saw another car on the opposite lane approaching at 30 centimeters per second, from your perspective, it would look as if it's coming at you at 50 meters per second. I'm sure you've all thought about that when you were like 8 years old, looking outside the car window whenever you were going out on a road trip or whatever. No? Just me? Okay then. Negative V1 final. Well, we don't know V1 final yet, and we also don't know V2 final, but I'm going to go ahead and distribute the negative sign. So this is just going to be, I'll write it as V2 final first minus V1 final after distributing that negative sign, and that's going to be 50 centimeters per second. Okay, so now I have this equation and this one, which I guess I haven't simplified yet. Let's do 10 times 20 is 200, and then 15 times negative 30 is negative 450. So 200 minus 450 is negative 250. So negative 250 centimeters per second equals 10 V1 final plus 15 V2 final. Okay, two linear equations. We've got a couple of options here. We can either do substitution or elimination. For elimination, I guess we could just multiply both equations by 15 and add them to each other. That works. If you want to do substitution, all you would have to do is add the V1 final over to the left and then plug in the result for V2 final, which is what I would usually do. But elimination looks like it wouldn't be too terrible over here, so let's try it. Let's multiply this by 15 and see what we get. Negative 15 V1. Oh, wait. No, I was about to make a fatal mistake. 10. Multiply by 10, because the other V1 final is over here. Negative 10 V1 final plus 10 V1 final, that cancels out. And then you've got 10 V2 final plus 15 V2 final is going to be 25 V2 final. And then 10 times 50 is 500 centimeters per second. Oh, wait, no, 500 plus the negative 250. Okay, my bad. 500 minus 250 is positive 250. There we go. Did I do all that right? Let's see, 10 times 50, 500, plus negative 250 is 250. 10 times V2 final plus 15 V2 final is 25 V2 final. And then negative 10 V1 final and positive 10 V1 final cancel out. Okay, perfect. So we can divide both sides by 25 now. 250 divided by 25, we get V2 final is equal to 10 centimeters per second. Note that it came out positive. Note that it came out positive, which tells me that my prediction up here was wrong. V2 final is actually to the right. Okay, now that I know V2 final, I can just plug it in and solve for V1 final. So let's see, where do I want to do that? I guess I'll do it up here. So if I plug in 10, I get 50 centimeters per second equals 10 minus V1 final. Subtract 10, divide by negative 1, 40 equals negative V1 final, which means V1 final must be negative 40 centimeters per second. So I did guess the direction correctly for V1 at the very least. 40 centimeters per second to the left. And there you go. So that's an elastic collision problem between two objects with two unknown final velocities. Let me see, do we have another one? We do have another one. I'll just read this one out loud and you can do it on your own time. So it says, a 25-gram object moving to the right at 20 centimeters per second overtakes and collides elastically with a 10-gram object moving in the same direction at 15 centimeters per second. Find the velocity of each object after the collision. That one is for you to try out, and I'm sure you'll find more in your textbook if you want more. I mean, you could just make up your own, although there is a danger with that. I'm pretty sure sometimes if you don't put in good numbers, you might get some sort of completely nonsensical answer. So be careful when trying to make up your own, like, masses and initial velocities. Just be careful about that. But that is elastic collision. Usually they will actually give you one of the final velocities and you only have one unknown to solve for if they're going easy on you. But in the worst case scenario, now you know how to solve it. Okay, how about inelastic collisions? Oh, we have somebody in the chat. Hey there. If you have any questions, feel free to ask as we go along. If it's something that I'm planning on covering anyway, then I'll probably just wait to cover it at the time that I plan to cover it. And if it's something that requires, more time and thinking, I might wait until the end of the stream, or might even just answer it later after the stream, like in a separate video or something, or under the comments section or something like that. Let me get this piece of candy. I think the sugar will help keep me awake. Oh my goodness, it's sticking to the wrapper. There we go. I have a whole bag of these candies from I think over a year ago at this point. I keep them in the fridge, so it's not like anything bad is gonna happen to them. But I typically go through, let me think, probably one piece every month or every other month. I try not to take in too much sugar, except of course, in the form of natural sugars, fruits and whatnot. Anyway, I think it is time to move on to the topic of inelastic collisions. Inelastic collisions. So inelastic collisions actually come in two categories. Inelastic collisions. They are defined by the simple fact that energy is not conserved in them. Inelastic collisions in general are collisions in which mechanical energy is not conserved. So if these two things collided and they collided inelastically, then the problem I would get would have to tell me one of the final velocities, because I wouldn't be able to use my second equation. This relative velocity relationship is only true when mechanical energy is conserved. So if the mechanical energy is not conserved, I can't use this anymore, which would mean that I wouldn't be able to solve a problem with two unknowns. I would have to have a problem where there's only one unknown. So basically take this same scenario, but let's say the book problem told you that object 1 ends up moving backwards at 30 centimeters per second, and then go calculate what's the final velocity of object 2. That would be an inelastic collision problem. And if you're not sure, I would by default assume that a collision is inelastic unless I am told otherwise. Unless I have additional information, assume all of your collisions are inelastic. Now, there's a special case of inelastic collisions. There's a special case called a perfectly inelastic collision. Perfectly inelastic collision. A perfectly inelastic collision is a collision in which the objects stick together after the collision and move as one. So a good example of that would be like the car crash scenario that I talked about yesterday, where two cars crash together and like the metal of their bumpers gets fused together in such a way that it requires a lot of force to separate them. That would be an example of a perfectly inelastic collision. Other examples of perfectly inelastic collisions don't even have to be that violent. Another good example of a perfectly inelastic collision would be something like somebody jumping up in the air and catching a ball that was flying towards them. Or let's say two people are having a snowball fight and they both throw their snowballs at the same time, and the snowballs hit each other and get smushed into one big snowball. That would be another example of inelastic collision. And also, because the equation doesn't really require any sort of, I guess, how do I word this? Because the equation doesn't really care about which side of the equation the combination of the two objects happens, because the equation doesn't care whether it happens before or after, things separating from each other is also a case of perfectly inelastic collision. So if you we'll get problems, for example, where somebody is stuck on a frozen lake and they happen to have their trusty physics textbook with them. And in order to get themselves to move, they have to throw their textbook to the right, causing them to move to the left. That is also an example of perfectly inelastic collision. It's just that you've reversed the right and left sides of the equation, so to speak, but equations don't care which side is on the right and which side is on the left. So yeah, things, I guess, uncolliding, so to speak, would also use the conservation of momentum equation for the inelastic collision case. Actually, it's the same equation whether the collision is elastic or inelastic or even perfectly inelastic. It's all the same equation. The only difference is that for perfectly inelastic collisions, since the two objects either before or after are going to move together, for perfectly inelastic collisions, here's what's going to happen. So let me write the basic conservation of momentum equation for two objects. Add more terms if you've got more than two objects, obviously. But if we take this basic equation, for perfectly inelastic collisions, if the two things combine afterwards, then V1 final and V2 final are going to be the same thing. So it would simplify to this. It would simplify to M1 V final plus M2 V final. Factor out the V final, you get M1 plus M2 all times V final, where V1 final equals V2 final. So we just call it V final without the need for the 1 or the 2. So this is if the two objects combine after the collision, and then if the two objects are already combined and they're having like a reverse collision, if they're separating, then the equation becomes this: M1 plus M2 V initial equals M1 V1 final plus M2 V2 final, where V1 initial equals V2 initial equals just V initial. You do not have to memorize these as two separate equations. These two are really just this equation at the end of the day, where two of your velocities just happen to be the same number. So to cut down on unnecessary memorization, to avoid confusing yourself, just remember the basic conservation of momentum equation, because it works in all cases. And with enough practice, you will mentally just make the quick jump from this to one of these. If you have a perfectly inelastic collision situation, just through sheer practice, you'll be able to just subconsciously figure out which side has a velocity that is the same for both objects, and you'll mentally start factoring it out just out of sheer habit. So I would not worry about deliberately trying to commit either of these two to memory. The basic version of the equation is really all you need. And I think that is it for introducing inelastic collisions. So let's go ahead and look for a problem or two that we can do. Okay, here's one. So it says a 12-gram bullet. Let me get a new sheet of paper. So it says a 12-gram bullet is fired horizontally into a 100-gram wooden block that is initially at rest on a frictionless horizontal surface and connected to a spring having spring constant 150 newtons per meter. Oh, we have a spring here. Interesting. The bullet becomes embedded in the block. If the bullet block system compresses the spring by a maximum of 80 centimeters, what was the speed of the bullet at impact with the block? If I had read ahead and noticed that there was a spring involved, I probably wouldn't have done this question, but you know what? Why not? Why not? Let's go ahead and do it. We were going to do this eventually anyway. Actually, let me pick a color that I haven't used yet today. How about you? Okay, so a 12-gram bullet. I guess we're going to have multiple scenes here. So scene 1, bullet gets fired at the block. And then, of course, there's a spring sitting here, waiting to be compressed. And I guess it's propped up against a wall. So that's scene 1. And then scene 2, so I'm going to call this scene 1. Pretend I'm a movie director or something. Scene 2, the bullet enters and gets lodged into the block. And the block starts moving to the right. Scene 2, here's the block with the bullet inside of it. And spring is still uncompressed. So that'll be my scene 2. Scene 3, the bullet block system compresses the spring as far as it can before the spring brings it to a stop. So scene 3, let's say it gets compressed all the way to here. So that'll be my scene 3. The bullet and block press on the spring and push it until the spring brings them to a stop. And then scene 4, of course, we know how springs work. This is going to get pushed back. And I'm just now realizing I forgot to do something. Oh, and I should probably draw the block like this. Yeah, forget what I was doing over here. That will be actually the spring. Yeah, that will be the spring back to its unstretched position. And forget what I did over there. Is that right? It's kind of lined up. I guess I probably could have gotten out a ruler to draw things more precisely, but I think my diagram is good enough to convey what's going on. Okay, let's go ahead and label some things. So I guess we're going to call this V. I'm going to use a lowercase b for the bullet and a capital B for the block. So lowercase b, bullet, capital B for the block. So V bullet, I'm not going to call it initial because I've got 4 different scenes here, so I think I will call it V bullet 1. Velocity of the bullet in scene 1, and velocity of the block in scene 1. The block is initially at rest, so we know that's going to be 0. This we do not know yet. In scene 2, velocity of the bullet in scene 2 equals the velocity of the block in scene 2 equals we don't know yet. Or do we? Hold on. Maybe we do. No, we don't. Not yet. Okay. And then for scene 3, all we know is this compression distance. The spring got compressed by x equals 80 centimeters, or 0.8 in meters. And at this point, the velocity of the bullet and block is 0. This is the point where the bullet and block are stopped. So VB3 equals V capital B3 equals 0. And then over here, the bullet and block are sent back at some sort of velocity. VB4 equals V capital B4 equals we don't know yet. Actually, it should be the same as whatever the velocity is here. If the surface is frictionless, then yeah, whatever kinetic energy the bullet and block had before colliding with the spring, they'll have the same kinetic energy after. Okay, so here we have a number of different steps. Some of those steps will be energy steps, some will be momentum steps. And that's what we have to work with. So between scene 1 and scene 2, come to think of it, I didn't do this for the previous problem, did I? I forgot to assess. We just went with the conservation of momentum equation and didn't really check for the condition for conservation. The condition is that net force external is supposed to be equal to 0. And if this surface is frictionless, then the only other external forces are the normal force and the gravitational force on each object, but those forces cancel out. So the net external force is 0. The only forces that don't net out to 0 are the forces that the blocks exert on each other, which are internal forces. Those are okay to have. Their net effect on the total momentum is 0, as we demonstrated yesterday. Anyway, now let's do that over here. So where is momentum conserved? Where is it not? Well, I guess momentum is conserved between scenes 1 and 2, because assuming no air resistance, there's nothing affecting the bullet. Well, okay, I guess technically there is a net gravitational force on the bullet. Okay, so here's where we're going to start using that hand-wavy logic that I was talking about yesterday. So yes, there is a net force of gravity on the bullet. So technically the net force external on the bullet is not 0. But we are going to argue that the effect of gravity is going to occur over a very short period of time. So whatever change in momentum is caused by gravity is negligible. And even if we didn't neglect it, the force of gravity is only going to cause a change in momentum in the in the vertical direction. So momentum in the horizontal direction is still conserved. The net force external in the horizontal direction on this bullet is still 0. Okay, what about the block? The block is going to have a normal force acting upward on it and a gravitational force acting downward on it. Those two forces are going to cancel out, so the net external force on the block is going to be 0. There's no friction here. So the only force exerted on the block or bullet between scene 1 and scene 2 is going to be just the forces that they exert on each other during collision. That doesn't net out to 0, and those are internal forces, so they are fine. Net external force between scene 1 and scene 2 is 0. Momentum is conserved between scene 1 and scene 2. Let me actually copy down, I forgot to write this. Mass of the bullet was 12 grams. I'm going to want to convert that to kilograms. 0.012 in kilograms. Mass of the block was 100 grams. I'm going to convert that to 0.1 in kilograms. and the spring constant of the spring is 150 newtons per meter. And because it's in newtons per meter, that's why I had to convert x over here from centimeters to meters. Anyway, if we go ahead and use conservation of momentum between scenes 1 and 2, then we've got m little b v little b initial, or in this case 1, plus m block v block 1 equals m bullet v bullet 2 plus m block v block 2. Okay, so that's going to be 0.012 times, well, we don't know yet, so I guess I'll just keep it as v bullet 1 plus 0.1 times, well, v block, the block is initially at rest, so that's going to be a 0, so that whole term is gone, equals, well, VB2 and V bullet 2 and V block 2 are going to be the same, so I can actually just factor this out and do MB, M bullet plus M block, which is 0.012 plus 0.1, so 0.112, all times, I guess I'll just call it V2. Okay, I have two unknowns here, so I can't really proceed yet. That's fine, let's continue. Let's see what else we can figure out. So that's what happens between scene 1 and scene 2. Between scene 2 and scene 3, there's no friction on this bullet block system, so it will move with no net force on it. It will move with constant velocity until it hits the spring. Once it hits the spring exerts a force on it. That force is an external force, which means the net external force on the bullet and block is not 0 anymore. Conservation of momentum does not apply between scene 2 and scene 3. However, something that does apply between scenes 2 and 3 is conservation of mechanical energy, because the forces acting on our object are normal force and force of gravity and spring force. Force of gravity is conservative and spring force is conservative, leaving only normal force as our non-conservative force. Okay, how much work is done by the only non-conservative force we have? How much work is done by the normal force? Well, the normal force is completely vertical, and the movement of the block and bullet, the displacement, is completely horizontal. So that's going to be normal force times the 0.8 meters times cosine of 90 degrees. Cosine of 90 is 0. So work non-conservative is 0. Mechanical energy is conserved here. So we will say 1/2, and I'll just treat the bullet and block as a combination here. 1/2 bullet plus block, 1/2 the combined mass times their shared speed squared from scene 2, plus their elastic potential energy before they hit the spring is 0, right? The spring is uncompressed in scene 2, so no elastic potential energy there. And for gravitational potential energy, there is no change in height, so I'll just say that the 0 height for gravitational potential energy is just on this table or surface, so that's another plus 0 if you wanted to include it there. Equals mechanical energy final, or in this case mechanical energy of scene 3. No kinetic energy because the bullet and block are brought to rest, so 0 kinetic energy, plus elastic potential energy we have is 1/2 kx squared plus the gravitational potential energy. If we set it to 0 for scene 2, then it must still be 0 for scene 3 since there's no change in height. In fact, even if you didn't set it to 0, whatever you set it to here, it'll be the same amount here. So even if this was not 0, if you assigned an arbitrary number to it like 1,000, it'll be 1,000 here and 1,000 there, and you'll cancel it on both sides anyway. So when there's no change in the height of an object, you don't really need to include gravitational potential energy in your mechanical energy equations. It'll just cancel out anyway. Okay, the 1/2 and the 1/2 are gone. And we've got the mass of the bullet plus the mass of the block was what again? 0.112. So 0.112 times V2 squared. We don't know what V2 is yet, but that's okay. We keep going. Equals kx squared. So k is 150. And x is 0.8. So 0.8 squared times 150. Well, it looks like we can solve for V2, finally. So 150 times 0.8 squared is 96. And then if I divide 96 by 0.112, I'm getting V2 squared is 857.1428571. If I take the square root of that number, I get 29.277. I'm going to round that to 29.28. So I'm getting V2 equals 29.28 meters per second. Okay, well now the problem is beginning to unravel. I think I said this before, but just in case I didn't, whenever you're faced with problems like these where you might not necessarily be sure where to start, just start from the beginning, like chronologically. Write out what happens first, what happens next, and write the equations between each of these scenes, so to speak. Even if you end up writing equations where you can't solve anything yet, so what? Just keep going. Keep writing more equations. Eventually you'll hit something that you can solve, and then from there you'll get something that you can plug back into a previous equation you wrote, which you can plug back into a previous equation you wrote, until it all just slowly but surely unravels. So if you're not sure where to start, start from the beginning. Start from the start. You can never go wrong starting from the start. Just have faith that the math will eventually work itself out. Now that we have this 29.28, they wanted us to find the speed of the bullet, the initial speed of the bullet. So if I go ahead and plug this back in over here, I should be able to do that. 0.112, so let's see, 0.012 v bullet 1 equals 0.112 V2, which we now know is 29.28. Oh, well, would you look at that. Really easy solve. 29.28 times 0.112 divided by 0.012. 0.112 times 29.28 is 3.27936 divided by 0.012 is 273.28. So V bullet in scene 1 was 273.28, and since we converted everything to standard units, this should be in meters per second. And yeah, the speed of a bullet being in the hundreds of meters per second is pretty realistic. That is something that I have seen in other physics problems before. I'm pretty sure we had some kinematics problems involving bullets where we saw such numbers. So I believe this result. So yeah, not the simplest example of inelastic collision, but we were headed towards this anyway. And I guess we never really did anything with scene 4, but with scene 4, VB4 is just going to be the same as VB2. It's going to be 29.28 if you work it out, because between scene 3 and scene 4, we can apply conservation of mechanical energy again. Notice, actually, I should point out, so kinetic energy in scene 2 equals potential energy in scene 3 equals, it's all kinetic energy again in scene 4. So kinetic energy of scene 2 and kinetic energy of scene 4 are exactly equal. So the kinetic energy stayed the same, but what did change was the momentum. So here's, I guess, another example you can add to that grid from yesterday. Here's another example where momentum is not conserved while mechanical energy is. So you can add this to that grid. Okay, let's have a look and see if we can find a simpler one. Okay, here's one. So it says a 1,200 kilogram car. A 1,200 kilogram car traveling initially with a speed of 25 meters per second in an easterly direction crashes into the rear end of a 9,000 kilogram truck moving in the same direction at 20 meters per second. The velocity of the car right after the collision is 18 meters per second to the east. What is the velocity of the truck right after the collision? And how much mechanical energy is lost in the collision? Account for this loss in energy. So we have a 1,200 kilogram car. Moving at 25 meters per second to the east. And it crashes into a truck. I don't know what I'm doing with those truck wheels. But that's the before picture, and then the truck was moving at 20 meters per second. Truck was moving at 20 meters per second in that same direction. So 1,200 kilograms versus 9,000 kilograms. Okay, the velocity of the car after collision is 18 meters per second. So after collision, it's moving at 18 meters per second. How fast is the truck moving? I drew this really badly. There's not even enough room to draw the wheels. Barely. What is V truck final? I assume it's going to be towards the right. Because, well, the car behind it was moving faster and it slowed down, so it lost some momentum to the right, which means that this truck must have gained momentum to the right. And if it was already moving to the right and you add more momentum to the right, then its final momentum should still be to the right. So I can say pretty confidently this time that this truck's final velocity is going to be to the right. Anyway, we need to calculate that final velocity of the truck, and we need to figure out how much mechanical energy is lost in the collision. So let's switch to, I guess we didn't really use red much today. So, condition for conservation of momentum is that net force external has to be 0. They didn't say anything about the road being frictionless, but that's okay, because we only need the momentum to be conserved during the collision, just immediately before and immediately after. So even if there is friction, again, more of that hand-wavy logic that I hinted at yesterday, if we just consider the very, very brief moment involving just before the collision, during the collision, and just after the collision, if it all happens within the span of like a couple milliseconds, then we can say whatever change in momentum is caused by things like friction and gravity, we can treat that as being negligible. We can treat that as having a negligible effect on the overall momentum. So the momentum, even if there's friction present here, is still kind of conserved. It would be another story if there was friction here and we had to consider what the velocity of the car is after friction takes away from this 25 meters per second. If that was relevant, they would tell us about it in the problem, and then we'd have to calculate, oh, this car is this many meters away from the truck, and during the amount of time it takes for this car to catch up with the truck and hit it, this much displacement occurs, therefore this much work is done by friction, yada yada yada. And so it collides with the truck at a velocity of, I don't know, let's say 22 meters per second due to friction slowing it down. If that was something they wanted us to do, they would give us more information. But assuming this 25 meters per second is the speed at which the car is moving immediately before the collision, then we can neglect effects like friction. We can neglect the effects of those external forces over that very short period of time. You can worry about things like that when and if you end up working for NASA, as I always say. So net force external is maybe not 0, but practically 0. 0-ish. How about that? Don't actually write this on your paper, by the way. The graders are going to look at you weird. Well, I mean, they won't look at you, but if they could see you while they were grading your paper, they would probably give you the look. Anyway, so we can go ahead and apply conservation of momentum here and be approximately correct. We would have M1 V1 initial, so that's going to be 1,200 kilograms times positive 25, I'm going to say right is positive, plus 9,000 kilograms times positive 20, since that's also to the right, equals M1 V1 final, so 1200 times 18, plus M2 V2 final, so 9000 times V truck final. I don't even have enough space to write it. I'll just say T comma F. Okay, this is easy enough. There's just one unknown. We can immediately solve for it. So we're going to do, let's see, 1200 times 25 minus 1200 times 18 is 1200 times 25 minus 18. 25 minus 18 is 7, so I'm going to have 1200 times 7 plus 9000 times 20 equals 9000 V truck final. And calculator time, 1200 times 7 is 8400, I believe. Yep. And then plus 9000 times 20 is a whopping 188,400. And then divide that by 9,000, and we get 20.93 repeating. So V truck final equals about 20.93 meters per second. It is faster, which is within my predictions. It has to be faster because if this car lost momentum and the momentum of the system is supposed to be conserved, then whatever momentum the car lost, the truck had to gain. So yeah, the truck speeds up, but not by very much because the truck has a lot of mass. So to gain the amount of momentum that the car lost, it doesn't have to speed up by that much. All due to the difference in mass. Typically in collisions, the more massive object experiences less drastic changes in its velocity. I think that just makes intuitive sense. And yet, ironically, trucks are actually a bigger danger to their drivers than those drivers would believe. But that's a discussion for another time. Actually, there's, what's the name of the YouTube channel? I think he did a video called These Stupid Trucks Are Killing Us, and the channel name was Not Just Bikes, I believe. So you might want to watch that video, actually. It's pretty relevant to this topic. So the truck video from Not Just Bikes, I'll have to remember to link it as like an iCard in this stream. It'll show up in the little I button in the top right corner, or I think now YouTube actually shows those in the description of the video. I don't know what YouTube is doing, but anyway, I will link to it if I can remember to do that. Now back to the problem. So we solved part A, find how fast the truck is moving after collision. Part B, how much mechanical energy is lost in this collision, and account for this loss in energy. Whenever you are asked to account for something, you're basically being asked to explain where the extra stuff came from, if you have extra stuff, or where the lost stuff went away to if you lost some stuff. In this case, we lost something. We will have some lost energy, and we need to explain where that energy went. Where did it get lost to? What did it do? So to figure this out, all we have to do is calculate the mechanical energy before and after and compare them. So let me see. Did I say kinetic or mechanical energy? Mechanical energy in general, but in this case it's going to be kinetic energy specifically because we are not experiencing any changes in height, so there's not going to be a change in gravitational potential energy. And I don't see any springs here being compressed or uncompressed, so we don't have to account for elastic potential energy either. So change in mechanical energy is equal to, in this case, just the change in kinetic energy. If I wanted to include the potential energy, gravitational, and elastic or spring potential energy, those are zeros here. So it's just change in kinetic energy equals kinetic energy final minus kinetic energy initial equals, and this is for the whole system, by the way, so it's going to be 1/2 mass of the car, final speed of the car squared, 18 squared, plus 1/2 mass of the truck times final speed of the truck squared, 20.93 squared. So that's the kinetic energy final, minus kinetic energy initial is 1200 times 25 squared in the case of the car, plus 9000 times 20 squared in the case of the truck. Let's go ahead. Oh, and I forgot the 1/2. I'll just put the 1/2 out here in the front. I'm not having a brain malfunction. You're having a brain malfunction. I'm kidding, I'm kidding. Then again, by this point in the school year, maybe the stress of AP courses has caused some of you guys to have brain malfunctions. Anyway, 1/2 of 1200 is 600, so 600 times 18 squared plus 4500 times 20.93 squared is that big number. I'll keep it saved on my calculator. And then we've got 600 times 25 squared plus 4500 times 20 squared is another big number. And if I subtract the two, the first one minus the second one, I'm getting negative 9307.95. I'm getting negative 9307.5 joules of, or no, not 0.5, 0.95 joules of energy. Or if you prefer, minus 9.3 kilojoules of energy. So yeah, we lost over 9,000 joules. It's over 9,000. And where did it go? Where did this energy disappear to? Well, I guess I should have drawn it a little bit better, but in the book, their after picture of the collision, they have the car rammed into the back of the truck, and it isn't looking so smooth anymore. So the energy went into the crumpling of the front end of the car. And also, the back of the truck is looking a little bit bent in their picture as well. So just the front of the car and the back of the truck being smushed. That's where that energy went towards. It went towards the term that you'll see in textbooks is deforming. The energy went into deforming the bumpers of the vehicles, deforming the bodies of the vehicles. Or they might even use the word deformation if you prefer a noun. Well, I mean, deforming can be considered a noun too, right? Anyway, I don't want to turn this into an English lesson. So that's a simpler inelastic collision problem. Now let's figure out what we want to do next. I guess it may be time for the ballistic pendulum. I mean, we kind of already had a sort of ballistic pendulum-like problem in this one over here. We can use a combination of conservation of energy and conservation of momentum to create mechanisms and devices that allow us to measure the speeds of bullets. We already did so in this problem, but there is a practical application called the ballistic pendulum that we might want to look at. So here is a basic ballistic pendulum problem. Let me find it. Okay, so it says a 7-gram bullet is fired into a 1.5 kilogram ballistic pendulum. The bullet emerges from the block with a speed of 200 meters per second, and the block rises to a maximum height of 12 centimeters. Find the initial speed of the bullet. Okay, so we're going to apply some fuzzy logic here yet again. But in case you haven't heard the term ballistic pendulum, basically, here's the setup. You have a bullet. It gets fired into a hanging block. It gets fired into a block that is hanging by a metal rod on an axle or just a rope or a string. I mean, a string probably would be too flimsy, so maybe the metal rope. Or did I say metal rope? Metal rod. A bullet is fired into a block that is initially at rest. Then either the bullet gets lodged in and then the bullet and block together rise to some sort of height, or in this case, the bullet just goes completely through the block and does not rise with it. The bullet just goes completely through the block and does not rise with it. And then the block, now having some speed, thanks to colliding with the bullet, the block now swings upward by some amount and gains some gravitational potential energy. So if I drew this well, and I don't think I did, good enough. So there is some little bit of height gained. And the bullet just goes off to wherever. In this third scene, we don't really need it anymore. It'll still be on the same path it was over here. Well, I guess gravity would curve its path downwards, but we don't care about the bullet after this point. So yeah, bullet collides with the block part of your ballistic pendulum. The block rises. We measure how high it rises, and then based on that, we can do some energy calculations. We can figure out how much potential energy, gravitational, does it have at the height that it reaches, and then from there we can work backwards and deduce what was its velocity when it first started swinging up, just after the collision with the bullet. And then from there, once we know how fast the block was moving after collision with the bullet, we can work backwards to figure out how fast was the bullet moving before the collision. And I'm going to solve it the exact same way that I did with this problem, which is I'm going to just write out the equations for each of my, between each of my scenes chronologically. We're just going to go chronologically. So what information were we given again? 7-gram bullet. So mass bullet is 7 grams or 0.007 in kilograms. Mass of the block, which I will symbolize with a capital B. The ballistic pendulum was 1.5 kilograms. And most of that mass is in the block part, not in the rope or rod part of it. Although we'll save the worrying about mass distribution once we get to rotational dynamics. That's where that becomes a little bit more relevant, especially for Physics C. And then the bullet emerges from the block with a speed of 200 meters per second. So here, I guess this is going to be, okay, so this is scene 1, scene 2, and scene 3. So over here, I'm going to say V bullet of scene 2. V bullet scene 2. I guess my B looks like a 6 over here. I don't know how to fix that. I mean, I curl the top part of my 6s. So I don't think it'll be that confusing if you're used to my handwriting by this point. But that's 200 meters per second is what they said. And then they say the block rises to a maximum height of 12 centimeters. H equals 12 centimeters here, or 0.12 if I convert that to meters. Find the initial speed of the bullet. That's the only thing they want. What is V lowercase b 1? That is the big question. Okay, so between scene 1 and scene 2, technically, the block starts rising even while the bullet is still going through it. But, I mean, if the bullet comes out at 200 meters per second, then I think it's safe to say it wasn't in there for very long, so changes due to the block rising while the bullet was still inside of it, we can neglect those effects. Again, worry about it if you end up working for NASA. So we can say what? Well, there's a force of gravity acting on the bullet, so there is an external force, but we're looking at a horizontal collision, so net force external in the y direction may not be 0, but net force external in the x direction on the bullet and the block most certainly is 0. So we can argue that momentum is conserved between scenes 1 and 2, at least in the horizontal direction, which is what we really care about here. So I can say mass bullet V bullet 1 plus mass block V block 1 equals mass bullet V bullet 2 plus mass block V block 2. And if I go ahead and substitute what I know, I'm going to have 0.007 times we don't know yet, VB1, plus 1.5 times, well, 0. The block is initially at rest, so that's a 0, equals mass bullet again is 0.007 times VB2 was given to us as 200 plus mass block is 1.5 times V block 2 we don't know yet. That's okay. We'll save this for later. Okay, now let's take a look at what's happening between scenes 2 and 3. So the bullet at this point is gone. It zoomed off to wherever. Maybe it hits a wall and stops. Hopefully it doesn't hit a person. Or next worst thing would be like hitting sensitive machinery and equipment that costs a lot of money to replace. That would probably be the next worst thing that the bullet could hit. But really, what happens between scene 2 and scene 3 is mainly focused on the block. So this block is going to have some sort of velocity now that the collision is over. It will have whatever this is, whatever this V block 2 is. And that means it's going to have some initial kinetic energy. And all that kinetic energy is going to disappear. It's going to rise and rise and rise until it comes to a stop at some maximum height. If it comes to a stop, that means its kinetic energy is 0 over there. And basically all the kinetic energy will have turned into gravitational potential energy. So let's see. Work non-conservative would just be what? Gravity acts on this block and tension acts on the block. As the block moves in some sort of circular arc, right? It's moving on like part of some circular path. So at all times, its displacement is tangent to that arc, and at all times, the tension force is perpendicular to that tangent, which means the work done by the tension force is always going to be 0 due to being perpendicular to the displacement at all times. I know some of you are probably tired of hearing me say that, but you might be thankful when reviewing for the big exam day. Let me switch colors. I'm getting tired of purple here. So work non-conservative is 0. The only non-conservative force we have between here and here is the tension force, which does no work. So work non-conservative is 0. We can just say mechanical energy final equals mechanical energy initial. So mechanical energy initial, 1/2 m block v block 2 squared, plus I'm going to say that this is my 0 height line for gravitational potential energy, so plus 0, and then plus 0 for elastic potential energy as well, or spring potential energy, as I usually prefer to call it, but I guess I've gotten in the habit of calling it elastic after saying it so many times in whichever stream I introduced it in. And then we have no kinetic energy. Once we get to scene 3, we do have gravitational potential energy, mgh, so that's m block g, and then the h is going to be the 12 centimeters. We'll plug in the numbers in a minute, and no spring potential energy. We can cancel out the mass of the block, not needed, and we can multiply by 2, so VB2 squared is equal to 2GH, so VB2 is equal to the square root of 2GH equals square root of 2G is 19.6, and then H is 0.12. So let's see what that is. Square root of 19.6 times 0.12 is about 1.5336, so I'm going to round that to 1.53. About 1.53 meters meters per second. Okay, now that we know this, we can take it and plug it back in here. And that will allow us to figure out the initial speed of the bullet. So 1.5 times 1.53 plus 0.007 times 200. 1.5 times 1.53 plus 0.007 times 200 is equal to 3.695, and then divide that by 0.007. And I'm getting, for V bullet 1, I'm getting 527.857. I'm going to round that to 527.86. V bullet in scene 1 is 527.86 meters per second. Pretty reasonable. Most bullets do seem to move in the hundreds of meters per second, and it also makes sense that it's higher than 200. It would have to be moving at higher than 200 meters per second, because once it collides with the block, it's going to slow down, it's going to lose speed. So that's another, I guess, intuitive check we can make. It does tick the box for must be greater than 200. So I don't see anything too alarming that would, prompt me to go back and double check my work. The number I'm getting seems reasonable. But always be in the habit of asking yourself if the numbers you're getting make sense. Okay, so that was the ballistic pendulum. Now let's go ahead and look at an example of collisions involving more than two objects, and then we'll do some two-dimensional collisions, and then we will wrap things up. Actually, I think there's going to be one more problem after that I want to add, and then well, hold on. Let me think. Actually, let's do that problem right now, because if I don't, I might forget to do it. Okay, so this next problem, I believe, involves some kinematics. So it says an 8-gram bullet is fired into a 250-gram block that is initially at rest at the edge of a table of height 1 meter. The bullet remains in the block, and after the impact, the block lands 2 meters from the bottom of the table. Determine the initial speed of the bullet. So I'll draw what they have. So they have, at 1 meter high, they have a table. And on that table is a block that's sitting at the edge of the table, and there is a bullet that gets fired at that block. The bullet gets lodged into the block. I'm not going to redraw the whole table, but the bullet gets lodged into the block like this, gets stuck inside the block, and at this point the block now containing the bullet has some sort of velocity. I guess we'll call that V little b2, which equals V big B2, which we can just call V2 in general. Over here, we'll call this V little b1, and for the block, it'll just be at rest. So I guess V big B1 equals 0. Okay, so that's scene 2. So scene 1, scene 2, and then scene 3. Here's the table, and then 2 meters away is what they said. Yeah, 2 meters away, for scene 3 over here, 2 meters away, the block with the bullet inside of it falls on the ground like so. Okay, you know what? I'll redraw the table. There, our table has legs again. Okay, similar to the previous problem and the one that we did 2 problems before that. We're going to have a collision step, a momentum step, and then the other step is actually going to be a kinematics step. A 2-dimensional kinematics step. Let's see what we can do here. So again, fuzzy logic. Yes, there's an external force on this bullet, which is the force of gravity, but if the bullet is moving really, really fast, the gravity barely has enough time to give it any downward momentum, and even if it did, this is a horizontal collision we're talking about, so we only need to worry about net external forces that would affect the horizontal momentum of the bullet and block system. So between scenes 1 and 2, other than the force of gravity, what other external forces do we have? Well, gravity and normal force on the block, but those cancel out. So yeah, net external force that is actually relevant to a horizontal collision is 0. And we aren't assuming any friction. If this block is on the edge of the table, even if the table has friction, the friction isn't going to have much time to act anyway, with the block already being on the edge. The block, as soon as the bullet gets in it, it's going to get off the table anyway. So friction, even if present, is also going to be a negligible effect here. Okay, so I'm going to write M bullet V bullet 1 plus M block V block 1. We already know from the previous 2 examples, well, not the previous 2, this one and the 2 examples before it, we know this is going to be 0, so I'll skip writing it out this time. I'm sure some people wish I did that the first 2 times as well. Equals mass of bullet V of bullet 2 plus mass of block V of block 2. Those are both going to be the same V, so I will just factor it out as a V2, and that leaves us with mass of bullet plus mass of block all times V2. If you have to write it as M bullet V bullet 2 plus M block V bullet V block 2, then by all means do it that way until you get used to these, and then you can do what I just did. Eventually you'll get to a point where you can mentally just jump to this as you're writing your equations. Anyway, that's our conservation of momentum step. Let me go ahead and substitute the numbers that I do know, which I forgot to copy down actually. So mass of the bullet was 8 grams, or 0.008 in kilograms, and mass of the block was 250 grams, or 0.25 in kilograms. Actually, I don't think it would have mattered here. I think if we had just kept these in grams, this problem would still work out, since we don't actually have to do any energy stuff here. I don't think we need to convert to standard units, because kinematics doesn't depend on mass at all, so it doesn't even care what the mass units are. But since I already did the conversion, we might as well. Okay, so that's going to be 0.008 times something we don't know yet equals, that's going to be 0.25 plus 0.008 is 0.258. And then V2 we do not know yet. Okay, so that's between scenes 1 and 2. Between scenes 2 and 3, we have some projectile motion going on. We know delta x is 2 meters, and we know delta y is how much? Let's see who remembers their kinematics. Is it 1 meter? No, it's -1 meter. It's downwards, and we typically use negative for the downward direction. Delta y is -1 meter. Okay, then I guess let's go ahead and solve for, we need to solve for the time it took to fall 1 meter. Starting with, I guess, Vy initial between here and here, Vy up here, so I guess this is V2x actually, and V2y would have been 0. The vertical velocity would have been 0 at scene 2. So let me think. Second equation would probably be best for us here. So delta y equals Vy initial times t, so V2y times t minus 1/2 gt squared, right? The acceleration is minus g, so plus negative g is minus g, and then the 1/2 from the equation that hopefully we still remember. And V2y is 0, so that's gone. So -1 is equal to -4.9 t squared. The negatives cancel out, divide by 4.9, and take the square root. 1 over 4.9 is 0.20408. If I take the square root of that, I'm getting about 0.4517. I'll round that to 0.452. I will say t is equal to about 0.452 seconds. I don't know why I circled that. We're not done yet. Okay, now that we know that, we can figure out what V2x is, because delta x is equal to Vx times t, or in this case, V2x times t. So that's going to be 2 equals V2x times 0.452. Divide by 0.452. So 2 divided by 0.452 is equal to 4.424. I'm just going to round that to 4.42. So V2x is equal to 4.42 meters per second. All right. And now that we have that, we can go back and plug it in here and solve for V bullet 1. So let me switch colors. 0.258 times 4.42 equals 0.008 times V bullet 1, divide by 0.008. So 0.258 times 4.42 divided by 0.008. I'm getting 142.545. V bullet 1 equals 142.545 meters per second. All right, there we go. So hopefully these problems have illustrated why all the chapters leading up to this one are still very much alive and relevant. Kinematics is still relevant. Force and work and energy, all of that is still relevant. Now then, let's talk about collisions involving more than two objects. So it's really not going to be that complicated. If you have collisions involving more than two objects, then you just add more terms to your conservation of momentum equation. I mean, you probably could have guessed that just from yesterday when we wrote out the conservation of momentum equation for the first time. When I wrote net force external 1 plus net force external 2 plus net force external 3 and so on and so forth when defining net force external for a whole system of objects. So if we have more than one object, all we do is, instead of m1 v1 initial plus m2 v2 initial and stopping there, we just add more terms. m3 v3 initial, m4 v4 initial, and so on and so forth, equals, and then we write just as many terms for after the collision. Now, the implication from this is that all of these objects collide at the same time, which is kind of unlikely. Getting two objects to collide with each other, that happens every day, even by accident. But getting three or more things to all collide at the exact same time? Much more difficult, much less likely to happen. But that's okay, because time is not really a factor in this equation. This equation doesn't care how much time there is between the collisions of all the objects that are going to be involved in whatever problem you have at hand. Even if the collisions happen one at a time between individual pairs of objects, this equation still holds true. And I'm going to have an example that actually illustrates that. So whether you just do your collisions sequentially, doing it like one pair of objects at a time, or you do it all at once like this, mathematically you get the same results. Mathematically, you will get the same exact results. So let's go ahead and look at this example in my book and see how that works. So it says we have 3 carts of masses 4 kilograms, 10 kilograms, and 3 kilograms move on a frictionless horizontal track with speeds of 5 meters per second, 3 meters per second, and 4 meters per second as shown in the figure, which I will draw for you in a minute. The carts stick together after colliding. I guess they have some glue on their edges or magnets or something. Find the final velocity of the 3 carts, and then part B, does your answer require that all carts collide and stick together at the same time? Well, I've already spoiled it for you. The answer is no, but let's prove it mathematically. So we have in their drawing, they have a 4 kilogram moving to the right at 5 meters per second, and a 10 kilogram moving to the right at 3 meters per second, and a 3 kilogram moving to the left at 4 meters per second. And all of these objects stick to each other after colliding, so these are perfectly inelastic collisions that we're talking about. And they are on a frictionless surface. So let's see, external forces would be, there's no friction, like I just said. Normal force and gravitational force, we've been through this a number of times before, they cancel each other out. So the only other forces remaining will be the forces that the blocks exert on each other, which are internal forces. So net force external on this system is going to be 0, which means momentum is conserved. So let's go ahead and compare the different scenarios that we could have. One scenario we could have is the 4 kilogram collides with the 10 first, and then that combination then collides with the 3 kilograms. The other possibility is that the 3 and the 10 collide first, and then later that combination collides with the 4. So let's show that both of those lead to the same result, and then let's also show that if we pretended they all collided at once, we would still get the very same final result. So M1 V1 initial. Let's say that these first two collide first, and M1 is going to be this, M2 is going to be this, and M3 is going to be this, just from left to right like I usually do. M1 V1 initial plus, yeah, I'll just call it M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. V1 final and V2 final would have been two unknowns, but they told us that the blocks stick together, so they're actually the same value, which means they're only one unknown. So that's fortunate, because with inelastic collisions we don't have a second equation that we can draw on. We don't have the energy equation at our disposal for this. So they thought very carefully when writing this problem for us. So we've got 4, I don't know why, well, I know why I wrote 5. 4 times 5 plus 10 times 3 equals 4 times, I'll just call it V final, plus 10 times V final. Okay, 4 V final and 10 V final is 14 V final, so we've got 20 and 30, that's going to be 50, so 50 equals 14 V final, so V final is going to be almost 4. 50 over 14, 3.57. V final is going to be 3.57 meters per second. Actually, maybe V final is not a good name for this. What would I call this? I guess I would call this V12 is the better way to name it. V1-2. The velocity of block 1 and 2 combined. Yeah, that's a better name for it. So I guess I'll correct it here as well. 1-2. 1-2. 1-2. And yeah, we can leave that alone. Okay. Now let's take this new block of mass 14 and velocity 3.57. Well, we already know 14 times 3.57 should be 50. So we've got the momentum of that, which is 50, plus the momentum of block 3, which is going to be, let's see, M3 times V3 initial, is going to equal M1 plus M2 V final plus M3 V final. They all have the same final velocity since they stick together and move as one. Let's see, so that's going to be 50 plus M3 V3 initial. That's going to be 3 kilograms times, be careful about this, -4. That's going to be 3 times -4 due to the velocity of block 3 being to the left. And then that's going to be M1 plus M2 is 14, and then plus M3, so that's going to be 17 V final. 14 V final plus 3 V final is 17 V final. 50 minus 12 is 38, and 38 over 17 is a little bit more than 2. 38 over 17 is about 2.235. I'll say, yeah, I'll do 2.235. So V final is about 2.235 meters per second. Okay, so that was one possibility. Another possibility is blocks 2 and 3 collide first, so let's take a look at that. Let's do another color. How about orange? So what if blocks 2 and 3 collide first? Let's see what happens then. So we would have M2 V2 initial plus M3 V3 initial equals, there we go, now it's writing a little bit better, equals M1 V2-3 plus, or no, not M1, M2 times V2-3 plus M3 times V2-3. So that's going to be 10 times 3 plus 3 times -4 equals 10 V23 plus 3 V23 is 13 V23. Let's see, 30 and minus 12, that's going to be 18. So 18 equals 13 V2-3. Divide by 13 and V2-3. Actually, we don't even need to do that division step given what we learned earlier. But just for the sake of figuring out what it'll be, I'm getting 1.3846. I'll just round that to 1.385. V2-3 is about 1.385 meters per second. Okay, and then next step would be this now 13 kilogram combination block colliding with this 4 kilogram block. So that would be M1 V1 initial plus, now it's a 13 kilogram block, it's M2 plus M3 times V2-3. It's 13 times V2-3. We already know that's 18. So let's use this number since it doesn't have any rounding errors in it or anything like that that could ruin the problem for us. And that's going to equal M1 V final plus this 13 kilogram combination times V final. And so I get 4 times 5 plus 13 times v23 is 18 equals m1 v final plus m2 m3 v final, or m2 plus m3 v final rather, not m2 m3, that implies multiplication. So 4 v final plus 13 v final is 17 v final. And 4 times 5 is 20. 20 plus 18 is 38. So 38 equals 17 v final. Oh, well, doesn't this look familiar? That was also 38 equals 17 v final. 38 divided by 17, I get 2.235 again. V final is 2.235 meters per second again. Well, how about that? And now, let's suppose that we treat them as if they collided all at once. Now let's treat them as if they collided all at once and see what math turns up from that. So if I do m1 v1 initial plus m2 v2 initial plus m3 v3 initial equals m1 v final plus m2 v final plus m3 v final. Then what I end up getting is, let's see, 4 times 5 plus 10 times 3 plus 3 times -4 equals 4v final plus 10v final plus 3v final, which is just 17 v final. 20 plus 30 is 50, minus 12 is 38. I still get 38 equals 17 v final. So I think with this I have illustrated my point. We can treat multiple objects in a collision as colliding all at once, even if that's not how it actually happens in real life. Mathematically, the conclusion we arrive at is the same. So that is collision between multiple objects. Now all that's left is for us to discuss collisions in 2 dimensions. Alright, so for collisions in 2 dimensions, I already gave you an idea of it yesterday. Basically, you just do the conservation of momentum equation twice. Once in the x direction and once in the y direction. And that's it. And sometimes you'll have problems where momentum is conserved in the x direction but not the y, or the y direction but not the x. In fact, that's kind of what we argued for some of our problems today, with our bullet having its momentum conserved in the x direction but not the y. Well, the bullet and block system having their momentum conserved in the x direction but not the y. So we've actually already been introduced to this logic. Now all we have to do really is just look at a few problems and get the hang of using that logic, and then we can call it a day. Actually, let me think. Wasn't there... There was something. A problem that, well, I think it'll be a problem that I leave as homework, but we'll see. A problem or two that might be of interest. Let me see if I can find it real quick, actually. I'm not even sure if it's in this book or the other book. Okay, I see one problem that involves some relative velocity that I will want to leave you with, and the other problem I think is going to be in the other book, where it's going to be a problem involving like sequential collisions. And come to think of it, maybe we should also do an example of an inelastic quote-unquote collision where two things are being separated from each other. I mean, I already talked about it, and the math is simple enough, but we didn't really look at an example of it. So I might do that as well. But first, let's go ahead and dig up a problem or two to illustrate two-dimensional collisions. So first up, I have, where did it go? Here it is. It says a 2,000 kilogram car moving east at 10 meters per second collides with a 3,000 kilogram car moving north. The cars stick together and move as a unit after the collision at an angle of 40 degrees north of east and a speed of 5.22 meters per second. Find the speed of the 3,000 kilogram car before the collision. I might actually be able to fit it in the bottom of this page. So we have 2,000 kilogram car moving east at 10 meters per second. So I'm just going to do a top view, looking at it like a helicopter from the sky looking down. I guess here, let's bring back the giant eyeball of physics. The giant eyeball of physics. So here we go. Just imagine the giant eyeball is in the sky and looking straight down at the cars from up above. So that's what I'm drawing, just a bird's eye view, I guess is what it's called. So here we've got, what was it again, 2,000? Yeah, 2,000 kilograms moving to the east at 10 meters per second. There's another car, unknown velocity, moving north, and this car is 3,000 kilograms. They collide, and after the crash, the cars are fused together, so they become this 5,000 kilogram wreck. This 5,000 kilogram wreck that moves at, what did they say? 5.22 meters per second at a 42 degree angle. 5.22 meters per second. Did I say 42? At a 40 degree angle north of east. So that would be north from east, so like this. So that's 40 degrees. So at a 40 degree angle above the east direction at 5.22 meters per second. Find the speed of the 3,000 kilogram car before collision. So this is V2 initial What is it? That is their question. So clearly, energy is not conserved here. These cars crashed. There's some energy lost in them deforming each other. We can't use energy here. As for momentum being conserved, well, they didn't really mention any external forces on the cars. I mean, I guess if there was going to be an external force, it would be friction, which might be counteracted by the thrust on the vehicles from their engines, at least until they collide. So yeah, those forces I guess would cancel each other out, and then the normal force and gravity on them also cancel out. So I'm going to say net force external is 0 here. And we can do, let's see, in the x direction, we've got m1, which is going to be this vehicle, times v1x plus m2 v2x equals, I guess this is going to be m1 plus m2. And I guess we'll call this v final x. And then for the y direction, m1 v1y plus m2 v2 in the y direction equals m1 plus m2 times v final in the y direction. Okay, m1 v1x, I do have a v1x over here. Object 2, its x velocity, at least its initial x velocity, is 0, so that's gone. I probably should have added initial on all of this. What am I doing with my subscripts? Here I have initial at the end and then the coordinate direction. Here I have final and then the coordinate direction. I need to introduce some sort of consistency to my subscript patterns. I guess I would prefer to call this VX final, actually. I guess the reason that I put the X after here is because I think of it as V final first and then take its X and Y components. I'll think about it, and by I'll think about it, I mean maybe someday, after several months, I'll fall into a new habit and stick with that. I mean, it still makes sense, and that's all that really matters. Anyway, the x component of v final, so that's going to be 5.22 times cosine of 40, so we'll throw that in there in a minute. And then over here, for the second equation, m1 v1 y initial, object 1 has a vy initial of 0. Right? It's just completely in the x direction here. And then that is just going to be whatever it is that we're trying to solve for. And then Vy final is just going to be 5.22 times sine of 40 degrees. So yeah, we should have everything we need in order to do all this. Do I even need to do anything in the x direction, come to think of it? Probably not. I think I can just use this equation alone. So m2, 3000, times v2y initial, which is just going to be all of v2 initial, equals m1 plus m2 is 5000, times v final in the y direction, that's just going to be 5.22 sine of 40 degrees. Yeah, I don't even need that first equation here. Okay, so 5,000 times, make sure your calculator is in degree mode. 5,000 times 5.22 sine of 40 degrees is a very big number, 16,776 and some decimals. And if I divide that by 3,000, I get 5.592. I'm going to just round it to 5.59. So V2 initial must have been 5.59 meters per second, give or take. And that's it. There is no second part to that. Okay, that was less work than I expected it to be. Now let's take a look at a more complicated one. So this one says a billiard ball moving at 5 meters per second strikes a stationary ball of the same mass. It's very important that they are the same mass for the conclusion that we're going to be drawing. A billiard ball moving at 5 meters per second strikes a stationary ball of the same mass. After the collision, the first ball moves at 4.33 meters per second at an angle of 30 degrees with respect to the original line of motion. Find the velocity, both magnitude and direction, of the second ball after collision, and was the collision inelastic or elastic? So this is what's called a glancing collision. This is what's called a glancing collision. So you have one object with some sort of, so this will be M1 with V1 initial, and it will collide with another object, usually at rest, but it won't be a head-on collision. It will be an off-center collision, right? Here's the center of this object right here, and you can see that they're not exactly, their centers are not exactly lined up. So what's that going to do? Well, that's going to cause them to split up. It's not going to be a one-dimensional collision anymore. One of these objects is going to get flung this way, while the other one is probably going to continue on to the right, but also be deflected upwards like that. That's what's called a glancing collision. And actually, come to think of it, I'm not entirely sure about the reasoning behind the name. I mean, I have a guess as to, well, hold on. Let me see if we can just Google it real quick. It's probably something really simple that I'm just missing. Why are glancing collisions called glancing collisions? Glancing collisions are called that because the objects involved collide at an angle rather than directly head-on, like a glancing blow. Okay, yeah, that was kind of what I was thinking, but I just didn't have the words for it. And I hate that I had to read that off of the stupid AI overview. Remember, kids, when you're doing Google searches, even if the AI result sounds right, you probably want to look at some of the other results first and compare it. But in this case, I think because the answer is reasonable enough, I don't think we need to double check it as aggressively this time. But, you know, be careful with those stupid AI results because they have been very, very wrong on numerous occasions. Anyway, back to our problem at hand. So this billiard ball is initially moving at 5 meters per second. So V1 initial equals 5 meters per second. And it strikes a stationary ball of the same mass. So I guess instead of calling them M1 and M2, I'm just going to call them both M. So this will also have a mass of M. After the collision, the first ball moves at 4.33 meters per second at an angle of 30 degrees with respect to the original line of motion. So this one moves at 4.33 meters per second after collision at a 30-degree angle with the original line of motion. At a 30-degree angle with the original line of motion. Find the velocity of the second ball after collision, both magnitude and direction, and then determine whether the collision was elastic or inelastic. For that, we're going to have to look at the energy. What color have I not really used much lately? I guess red. Okay, let's figure this out. So we have M1 V1 initial, so that's just M times V initial. This is in the x direction, so M V initial in the x direction is M times 5 plus M times 0 plus the other M times 0 equals whatever this is. I guess I'm going to call it V2 final. And it's going to have components in the x direction and the y direction. And it's going to be at some unknown angle. Let's call it theta. And so this is going to be V2 final cosine of theta over here. And then for this vertical one, it's going to be V2 final sine of theta. This is looking awfully crowded. I probably should have planned a little bit better my placement of this V2 final. And then over here we're going to have something similar. We're going to have 4.33 cosine of 30 and 4.33 sine of 30 degrees. So in the x direction, I just want the x components. That's going to be m times 4.33 cosine 30 for the first one, plus m times whatever V2 final is, cosine of theta. Okay, and then in the y direction, well, in the y direction there was no initial momentum for either of them, so m times 0 plus the other m is also times 0 in the y direction equals the first m times 4.33 sine of 30 plus the second m times negative V2 final sine of theta. Because V2 final is going to be in the downward direction, since I already called V1 final a positive. Since I'm already making this positive, this one will have to be negative. Okay, let's see what we can do with this. So the m's cancel everywhere. I can just divide the whole equation by m, and the m's are gone. Let's see, so 5 equals 4.33 cosine 30 plus V2 final cosine theta, and then 0 equals 4.33 sine of 30 minus V2 final sine of theta. Well, two equations and two unknowns, my two unknowns being V2 final and theta. We can try to eliminate the V2 final, or we can try to eliminate the theta. I think we should try to eliminate the theta by squaring and adding. Let's try and eliminate the theta by squaring and adding. So what I want to do is, how do I want to go about this? I guess I will get the V2 final terms alone. So subtract 4.33 cosine 30 on both sides. 5 minus 4.33 cosine of 30 degrees. And that's going to equal V2 final cosine theta, and then I guess add V2 final sine theta over to the 0. I'm going to write it flipped, so I'm going to write it as V2 final sine theta on the left, or sorry, on the right, and keep 4.33 sine of 30 degrees on the right. Right, on the left. See, I'm even confusing myself with this. And then I just want to square both sides and add. So if I square this and I square this, I don't think this is actually good notation, but okay, we'll do this. There, that's better. If I square both sides of both equations and then I add the two equations to each other, then I get V2 final squared cosine squared plus V2 final squared sine squared. You'll factor out the V2 final squared and get sine squared plus cosine squared equals 1. So that's going to be just V2 final squared. V2 final squared equals, what's this going to be if I put these together? I want to actually continue this without plugging in the cosine and sine 30 just yet. I want to see what I can get from this. So that's going to be 5 squared, which is 25. Minus 2 times 5, so minus 10 times 4.33 cosine of 30 plus 4.33 squared sine squared of, no, not sine squared, cosine squared of 30. Sorry, that's an unreadable mess. It's supposed to say cosine. So that's the top part, plus 4.33 squared sine squared 30. Okay, and then this simplifies. 4.33 squared cosine squared plus 4.33 squared sine squared, basically the same thing that happened over here. Cosine squared plus sine squared will add up to 1, and the 4.33 squared that was factored out just remains alone. So we're left with 25 minus 10 times 4.33 cosine of 30 degrees plus 4.33 squared equals V2 final squared. And is there anything I can do with this that would give me like some sort of shortcut formula? That's what I'm trying to look for, and that's why I'm trying to avoid plugging in this cosine. Because I feel like I was able to derive something with this in the past, but I'm blanking on it right now. So we've got V1 initial squared and V1 final squared. So we've got V1 initial squared plus V1 final squared. And then we've got minus, this is 2 V1 initial V final cosine of, I don't want to call it theta, let's call it cosine of phi, where phi is just that 30-degree angle, equals V2 final squared. I feel like there's something I can do with this. If I put all of these together, oh wait, no, I can't because of, I can't because of that cosine. I feel like there's something here, but it's not coming to me right now. I feel like there's something that we can prove here. Anyway, let's go ahead and actually plug in the numbers then and see what we get for V2 final. So for V2 final, the value that we get is 25 minus 10 times 4.33 cosine 30 plus 4.33 squared is almost exactly 6.25, and then if I take the square root of 6.25, I get 2.5. So V2 final is equal to 2.5 meters per second. That's the magnitude. And then as for the direction, we can just plug this in anywhere. Let's plug it in over here. So 4.33 sine of 30 equals V2 final, which we now know is 2.5, times sine of theta, and solve for theta. So 4.33 sine 30 divided by 2.5, and then take the inverse sine of that, and we should get a result that is rather surprising, 59.997, or in other words, 60 degrees. Theta is equal to 60 degrees. What's special about this being 60 degrees, apart from it being a nice round number? How does it relate to the angle at which the first object was deflected? Well, if this was deflected at 30 degrees, and this one was deflected in the opposite direction at 60 degrees, then that means the angle between them overall is 90 degrees. That's something special that only happens in a collision where one of the objects is at rest and both objects have the same mass. As for the proof, I feel like I have the beginnings of it here, but I'm forgetting something. I'm missing something here that I should be able to take advantage of, but I'm not seeing it, and I don't know why. So I'll have to play around with that later. Actually, maybe the thing I'm missing is the next part of this problem, which says, was the collision inelastic or elastic? Well, to determine that, we have to take a look at the kinetic energy and see what it was before versus after. Well, mechanical energy to be more precise, but since there's no springs and no gravitational potential energy changes, we're assuming that this collision happens on the surface of a table, so there's no change in height. Actually, not assuming, we were told they're billiard balls and you don't play with those unless it's on a pool table. So, yeah, just kinetic energy. 1/2 mv1 initial squared plus 1/2 m. Actually, the 1/2 cancels out everywhere. But yeah, plus 1/2 m v2 initial squared, which was 0. Is it equal Actually, no, don't use an don't even use an equal sign. Just subtract. Actually, I should do final minus initial. Hold on. So this stuff is subtracted from the final kinetic energy, which is 1/2. Oh, then I guess the 1/2 isn't going to cancel out. Is subtracted from 1/2 m v1 final squared plus 1/2 m v2 final squared. Let's see. So the 1/2 m can be factored out of everything, and we can just compare v1 final squared plus v2 final squared and v1 initial squared plus v2 initial squared. So v1 final squared plus v2 final squared. 4.33 squared and 2.5 squared. If I add those, 4.33 squared plus 2.5 squared is 24.9988, or 24.9989 there. So that's going to be 25 essentially. So 1/2 m times 25. So that equals 1/2 m times 25 minus, this is going to be just 1/2 m times, well, that's 0, and v1 initial was 5, so 5 squared, oh, would you look at that, is 25. The mechanical energy is actually conserved in this collision. How about that? The mechanical energy is actually conserved, and I think that is the next piece of the puzzle that I need, combined with this equation, to derive a proof that when the masses are equal and when one of them is initially at rest, the sum of the angles the sum of their deflection angles, as they're called, because it's the angle by which they deflect from the original line of motion, the sum of their deflection angles would be 90 degrees. I think if I combine this equation with the conservation of energy equation, now that I know the collision is elastic, I think if I combine those two pieces of information, I should be able to get some sort of proof that phi plus theta is equal to 90 degrees. I'll try and work on it and see what I can figure out. But that is it for this problem. Now let me go back to, I guess I will leave this one as homework. And, well, I'll leave this one and another one as homework that we can discuss real quick at the start of next session, which will probably be the usual Sunday, but there is a chance that I might be able to squeeze one in on Saturday as well. We'll see. So this one says, a 45 kilogram girl is standing on a 150 kilogram plank. So I'll draw it over here. "45 kilogram girl standing on a 150 kilogram plank. The plank, originally at rest, is free to slide on a frozen lake, which is a flat, frictionless surface. So the plank is on ice and the friction is negligible. The girl begins to walk along the plank at a constant velocity of 1.5 meters per second to the right relative to the plank." So velocity of the girl relative to the plank is 1.5 meters per second to the right. To the right. Part A is asking, what is her velocity relative to the surface of the ice? So what is her velocity relative to the ground? And part B, what is the velocity of the plank relative to the surface of the ice? So what is the velocity of the girl and of the plank relative to the ground is basically the question. And that's all the information you have. I'll give you a little bit of a hint. This is a sort of collision. This is one of those, we didn't really get to do an example of them today, and I guess it's unfortunate that your first example is one that involves this added complication of relative velocity being thrown in, but this is what I talked about when I called it, I guess, two things uncolliding. It's an example of a perfectly inelastic collision where, actually, wait, I think energy might be conserved in this case. But anyway, this is what you would want to use. Just, again, like I said before, you can just use the basic conservation of momentum equation, and you don't really need to memorize these other two separately, but ultimately you're going to get something like this. They both start with the same V initial, which is 0, and then the girl moves to the right, which means the plank moves to the left by some amount. So they start with a total momentum of 0, and their final momentum must also add up to 0. Which makes sense, because if the girl has positive momentum to the right, the plank would have to slide left and have a negative momentum. But yeah, try and work that one out. Remember what I taught you about relative velocity, and this should actually give you a second equation that you can use in combination with your momentum conservation equation, so that you can solve for your two unknowns. So there's that, a problem involving relative velocity and perfectly inelastic collision. And then the other thing I wanted to give you was in my other book. Let me dig it up. I think it also uses relative velocity, actually. Let me see if I can find it. Momentum. No, that's rotational stuff. Here we go. Momentum. Where are you? Here we go. So the other problem looks something like this. So it says you have two 22.7 kilogram ice sleds. You have two 22.7 kilogram ice sleds. So there's one of them. And there's the other one. And we have, they're placed a short distance apart, one directly behind the other. Then you have, so these are 22.7 kilogram sleds. So this thing is 22.7 kilograms, and this thing is also 22.7 kilograms. And then they say a 3.63 kilogram cat standing on one sled jumps across to the other and immediately back to the first. Both jumps are made at a speed of 3.05 meters per second relative to the sled. Or rather, relative to the sled the cat is standing on when the jump is made. Find the final speeds of the two sleds. So you have a cat. I'm just going to draw a cat head. So you have a cat who is standing on this sled, jumps off of it onto the other sled, then turns around and jumps back onto the first sled. It makes two jumps. The first jump is made with the cat's velocity relative to the sled being 3.05, and then when the cat turns around and jumps again, the cat's velocity is again 3.05 meters per second relative to the other sled. So the difference is that it's going to be a relative velocity of 3.05 to the right in the first jump and 3.05 to the left for the second jump. And the question is, find the final speeds of the two sleds. So v cat relative to each sled, at least the magnitude of it, is 3.05. And remember, one of them is going to be negative depending on how you're going to define your directions. And what else? Mass of the cat was 3.63 kilograms. Let's write that down. And the question is, V sled 1 final equals what? And also V sled 2 final, what is it equal to? That is a pair of what I would call sequential collisions. Two collisions happening in sequence. Now, because of the relative velocity kind of mucking it up, I don't know if just treating it as a 3-object collision is going to work here. Actually, I never thought to try it that way. I'll have to play around with this myself if I can remember to do so. But yeah, there you go. There's two questions. I imagine this cat one is going to be a little bit tougher just because of the amount of work, if nothing else. But if you sit down and think about it slowly and carefully, you should be able to do it just fine. But yeah, those are going to be your 2 questions for homework, and we will address them at the beginning next time. So apart from these 2, of course, you can go through the textbook. If you don't have your own textbook from your own class, you can use the OpenStax textbook linked in the course plan. The course plan is linked in the description for those of you who are new here. It might not have the best problems, but it's better than having nothing. So definitely look through the problems, at least the ones that I recommended in the course plan, the ones that are listed there. Make sure you can do all of those, and once you're good there, try to find more challenging problems. And yeah, just keep testing yourself. But that is the end of the momentum chapter. We did it all in 2 episodes, 2 streams. So next time, in addition to answering these 2 problems, we are going to start the topic of uniform circular motion and gravitation. I imagine the next stream will mostly be focused on the circular motion, probably the next 2 streams. Actually, let me think. No, I'm probably going to dedicate just 1 stream to the basic circular motion, and then the second and third stream will probably be more gravitation focused. I don't know. I'll figure it out. I mean, I'm going to cover what I want to cover regardless of how much time it takes, but in the interest of keeping things somewhat organized, I would like to kind of just predict what I can squeeze into the next stream. But yeah, that will be it for today. If you have questions, comments, concerns, whatever, you can post in the comment section, or you can come to the next stream, which I will put on the schedule for Sunday, although there might be a surprise one on Saturday, so keep your eyes out for that. If I do decide to do one for Saturday, I will probably put it on the schedule. Or maybe I'll just stream without putting it on the schedule and it'll be just a complete surprise, who knows. But usually I plan at least by the day before if I'm going to make changes and put things on the schedule. So keep an eye out for that if you want to catch it live. If you would rather just wait until everything is recorded and timestamped and all that, then by all means. Speaking of, I still have to timestamp the previous stream. I haven't done that yet. I'll probably get around to that tomorrow night for both this one and the previous one. So yeah, I think that is everything. Hope you learned something useful. Hopefully this gave you something better than whatever you were getting before, whether you have a teacher or not. And yeah, I guess that's it. Class dismissed.